Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to talk about investigating limits conceptually. You should have already watched my videos on the basic concepts of limits, finite limits at finite points, and then single-sided limits. You should also know about neighborhoods, infinities, and the fact that some limits just do not exist. Now we're going to really start getting into faster ways to investigate really specific limits. Not all limits can be done this way, but what we're going to learn here is a nice skill that you're going to use for the rest of calculus. So the final non-rigorous method for evaluating limits, at least for now, there are actually 3 other methods, but let's just focus on this for right now, is the best of the group. So far, the way we've investigated limits would be via tables of values, which is the absolute worst way to evaluate a limit. And then the second way was via graphing. Again, not the best way to evaluate a limit. But now we are going to go through a conceptual investigation of how you would evaluate a limit. Now, I want to just tell you right now, this is not the theoretical way you would evaluate a limit, but it is the way that you're going to visualize limits to speed up your evaluations. It relies heavily on your knowledge of the graphs of the functions you're dealing with. And this is why the trig and the algebra prerequisites for calculus are so important. There's no way we can review those in calculus. If you need to review how to graph or what the graph of a logarithm is or the secant or something like that, please see my video series for trig and algebra. But I'm just letting you know, if you do not know those by heart, it's going to be very, very difficult to pass a calculus course. Now, before we dive into the meat and potatoes of this, let's start by discussing rough values of the following fractions. And I have 4 fractions in this page to talk about. So the first one is what happens when you have a finite number over a massive number. This is the easiest of the group. So remember, when you're dealing with a limit, it means that you're dealing with a function that's moving, that's approaching something or running off to infinity or something like that. And so you'll have these values that increase or decrease or stay stagnant, whatever it is. And you want to be able to determine, especially if you have fractions, what those values will tend to. So think of any finite number you want. Let's say, well, just close your eyes and think of a finite number. I will say pi. So think of the number pi. That's finite. And think of some massive number, like 1,000,000. That's pretty massive, I suppose. It's not actually massive in the scale of the universe, but whatever. But if I said I have pi over $1 million, that is nothing. That's less than a penny. Okay, so I have very little. So this is approximately 0. I mean, it's not 0, but it's close to 0. And the whole point of that statement is if you have a finite number over any massive number, the reality is that that will tend to 0. Now, I do want to mention here that when I say finite number, I'm saying that this guy in the numerator is going to park itself at, let's just say, some finite value. It could be very large, but it could be like, let's say, 1 trillion. But the denominator being massive tells me that that is going to grow and grow and grow forever and ever and ever. It's going off to infinity, essentially. So even if the numerator is finite and massive as well, the main thing is that the denominator is going to be more massive. What about the second case? What if you have a massive number, something running off to infinity or negative infinity, over something finite? We'll start writing down some examples for yourself. So something massive like 1,000,000 over something finite. Now, I do understand that 1,000,000 is also a finite number, and in that case, it would be 1, that ratio would be. But the reality is when I say massive, I mean this thing keeps growing. whereas that denominator will park itself and stop after a while. So this numerator is just going to continually grow. And when you look at that fraction, you can easily see that even if you cancel zeros between the numerator and the denominator, the reality is that fraction is going to be absolutely massive, right? If you cancel some zeros, let's say cancel 6 zeros between top and bottom, you still get this very massive number. What is it? 1 quadrillion? Yeah, I think so. Million, billion, trillion, 1 trillion. There we go. So it's still a very massive number. So the reality is that if you have something running off to infinity in your numerator and something locked into a finite value in your denominator, that will tend to infinity. It might be plus or minus infinity. It just depends on if that massive number is positive or negative, or if that finite number is positive or negative. The rules of that arithmetic still apply. So negative over negative is still positive. Positive over negative is still negative, that type of thing. Those rules still apply, but the main thing to note is that the ratio itself will grow without bound. Let's take a look at the third case. What if we have a finite number, again, we'll take the number pi, over something that's almost zero. So pi over something that's near to zero. Now let's think about a number that's close to zero. A lot of people will say like 0.00001 or something like that, right? And if you think about that number, let's see, this is the tens, 100,000, 10,000. This is the 100,000 place right there. So this is the same thing as saying I have pi over 1/100,000th. Now, from your arithmetic classes, you should know that that is the same thing as 100,000 times pi, right? This is a hinge right here, and this rotates up top. And so this ends up being a massive number. So when you have a division by something that's near to zero, and you have a finite number up top, that value will tend to something massive, specifically infinity, plus or minus, we just don't know, but some level of infinity. Again, this is a theme with this page, is that we're just taking examples to see how these fractions work out. You will need to really understand this process because it's going to be in every section you work in calculus. You have to know how these fractions work out. Now, the very final one is, I think, actually pretty easy, right? So you have something that's near to zero over something finite. Well, that's something like 0.00001, that's near zero, over something finite like 5. Well, still, that's basically 0 on top divided by 5, that's roughly 0. So this is going to tend to 0. That all being said, we are going to use that information as a basis for helping us conceptually investigate the value of limits. Instead of graphing or building a table, in fact, determine the value of the limit using descriptive concepts. Well, here's how I would do this if I was a student in a course. I'd first start by saying, okay, the limit as x approaches 3 of, I would just rewrite this very quickly. There's a specific reason why I'm doing this. And I would say that that numerator is tending to. This is how I notate it. This is how a lot of people notate it, in fact. But that numerator, as x approaches 3, is approaching 1 minus 3, or a negative 2. The denominator, on the other hand, is approaching 3 minus 3 squared. Now, it's not actually becoming 0, but it's approaching. That's why I'm using these arrows. Notice I'm not using an equal sign because it does not equal 3 minus 3. It's approaching 3 minus 3. That's very important. So it's approaching 3 minus 3, so it's approaching 0, but because it's being squared, and that's an important thing here, it actually is very important to note this. Because it's being squared, it's approaching 0 from above, from the positive side of 0, because it's being squared. I have a finite number divided by something really, really small, something near to 0. Well, on the previous page here, we already said if we have a finite number over something that's almost 0, that's going to be some level of infinity. And we're going to use these signs of those numbers to tell us if it's plus or minus infinity. So we have a finite number of negative 2, which is negative. over a finite number, something approaching 0 but positive. So we have a negative over a positive. Our answer will be negative, and we know it's going to be infinite because, again, finite over something that's near to 0 will be infinite. This is a conceptual investigation of that limit, and a very nice, quick investigation, something you really need to get used to. Now, I did say that the power being squared on that denominator was very important, and here is why. So this is the next example. Investigate the same limit, actually, right? It looks very similar to the previous problem. The only difference is this power. It's now a third power instead of a second power. So I'll write down what I did before. And just as I did before, I'm going to say that that numerator right there is approaching, it's not equal to, but it's approaching a -2. And that denominator, it's approaching some type of 0, but unfortunately, we don't know what type of 0 because it's approaching 3 minus 3, but it's not exactly 3 minus 3. And when you cube it, it doesn't immediately become positive. So I'm going to put a little question mark here because it will take on one of two values. I'll showcase this by writing the limit as a single-sided limit. Let's look at the limits from both the left and the right-hand side of 3, and you'll see something very special here. Again, from the left side of 3, still that numerator is still approaching, not equal to, a -2. The denominator, on the other hand, is approaching 0. It is true. However, think of a number that's slightly less than 3, like a 2.9. Subtract 3 from that, and that's a negative number. It's near to 0, but it's negative. And so we are then going to cube it, and it still will remain negative. So this is going to approach 0, but negative. And what does that mean? Well, we have a finite number in the numerator, and we have something super small in the denominator. So we know that this limit is going to be some level of infinity. And because that numerator is negative and the denominator is negative, negative over a negative is positive. So we happen to know that this limit, at least the left-hand limit, is going to be positive infinity. Now we need to investigate the right-hand limit. And what we're using here is that theorem that we had introduced in the last video, this guy right here, where we said that if the left and the right-hand limits are the same and they equal L, then the limit, the overall limit, must also be L. So I'm just checking in the problem that we're working on that the left and the right hand limits are the same. And that's often required in calculus to check both left and right hand limits. In this case, if we take the limit as x approaches 3, but from the right hand side, again, our numerator is approaching, not equal to, a -2, and our denominator is definitely approaching a 0, again, not equal to that. But now think of a number greater than 3, like 3, slightly greater than 3, I should say, like a 3.01. Well, when you plug in a 3.01 for x and subtract 3, it's still positive. It's near 0, but still positive. And when you cube it, it's still near 0 and positive. So our numerator is approaching, not equal to, but approaching a negative finite number. Our denominator is approaching, not equal to, but approaching 0, but positive. A negative number divided by a positive number is negative, and finite over near to 0 is going to be infinity. Notice the left-hand limit and the right-hand limit, these are not the same. Therefore, the overall limit, the original limit we are being asked to evaluate, does not exist. This is that elusive does not exist example. The value of this limit is not finite, nor is it infinite. It is just non-existent. Now, a lot of students will ask, how do I know when to split into checking for left and right hand limits, and when can I just barrel forward and not check left and right hand limits? Well, I knew I had to check left and right hand limits at this step right here, because as x approaches 3, this denominator tends to 0, totally true. However, it could be negative or positive, right? I don't know what side of 0 it's approaching. And when you cube it, it still could be negative or positive. Compare that to our previous example, where again, the denominator was approaching 3 minus 3 or 0, but you're squaring that. And so it's always going to approach a positive side of 0. So there was no question in this case. I didn't have to break it apart. But the other case, the more recent case, this guy right here, it was very important for me to break it apart because, well, there are two cases. One where our denominator is positive and one where our denominator is negative. Now, this is one of my favorite examples early on in calculus because this really drives home the ideas that you need to have in mind or the level that you need to be at when you're entering into calculus. Determine the value of this limit using descriptive concepts. So again, not building a table of values and not graphing it. When I say not graphing it, in reality, I'm not going to graph the overall function, but every once in a while, I might sketch out a graph of something to help me out. So let's see, as x is approaching 0, 2 minus 2 raised to the 1 over x power. Well, one thing I know, no matter what x is, that is always 2. No matter what you allow x to be, that number will always be 2. So that is not going to be touched by our limit. That's a little thing called a limit law that we'll learn in the future, actually pretty soon. But for right now, just note that this value of 2 is concrete. The other 2, this guy right here, well, that is going to change because it has an x attached to it. And if you think about its exponent, always follow the order of operations and zoom into the innermost object. That's this piece right here. Its exponent, that 1 over x, its value just depends upon what side of 0 that x is on. If x is on the right-hand side of 0, well then 1 over x takes on one value. If x is on the left-hand side of 0, 1 over x takes on a different value. Let's see how I arrive at that statement. Here we have the left-hand limit of 2 minus 2 raised to the 1 over x power as x approaches 0, again, from the left. Well, as x approaches 0, but from the left, we know we have a finite value here divided by 0 or something approaching 0. And so therefore that fractional exponent, it is approaching some level of infinity. It's a positive 1 in the numerator and a negative 0 or something that's negative but near to 0 in the denominator. So that exponent is approaching positive or negative, which is negative infinity. Again, finite over something super small like 0 is going to be infinite. Now you could be very rigorous with this. You could say as x is approaching 0 from the left, 1 over x is approaching negative infinity. Then you're going to zoom out and look at the 2 to the 1 over x. So as 1 over x is approaching negative infinity, 2 to the 1 over x is approaching. Well, let's talk about this. As the exponent is approaching negative infinity, well, that's like 2 to the negative large number, right? Conceptual investigation here. You know laws of exponents. That's just going to be the same thing as 1 over 2 to the large power, right? You can rip off the negative exponent and drop that 2 to that exponent downstairs. And here we have that case where we have a finite value up top, and in the denominator, we have an incredibly massive number. We know that's going to tend to 0. Again, as 1 over x, the exponent, goes to negative infinity, 2 raised to that very negative large power, it's going to be 2 raised to a negative large power, which is 1 over 2 to a large power, which is 1 over a massive number, which is basically 0. And as 2 to the 1 over x approaches 0, 2 minus 2 to the 1 over x, which is the limit we're looking at, is approaching 2 minus 0, or in other words, 2. And so the left-hand limit is 2. That's a good conceptual investigation, but we're not done because we have to look at the right-hand limit. Notice this limit is the total limit, so I'd like to find out the left and right-hand limits are the same. So let's go ahead and write down the right-hand limit. And again, what I'm going to do is do it in pieces. I'll work from the innermost object to the outermost object. The main condition is that x is going to 0 from the right-hand side. So as x goes to 0 from the right, 1 over x, well, that's 1 over something approaching 0, so that's going to be infinite, and positive 1 over positive 0, that is approaching positive infinity. Now that I'm done figuring out what 1 over x is approaching, let's figure out what 2 to the 1 over x is approaching. As 1 over x approaches infinity, 2 to that power, well, 2 to the infinite power is 2 to a massive power. Well, that's obvious. That should be obvious to you that will approach infinity. 2 to a massive number, that's a massive value. Well, now that we know where 2 to the 1 over x is tending, let's look at 2 minus that. So as 2 to the 1 over x approaches infinity, 2 minus that 2 to the 1 over x, well, again, 2 to the 1 over x is approaching infinity, so that'll be 2 minus basically infinity. Well, 2 minus infinity is a negative infinity, right? You have the number 2, you're losing an infinite amount of values, so it is going to be negative infinity. And therefore, we've shown conceptually that our limit, the right-hand limit, is equal to negative infinity, which, by the way, is not the same thing as the left-hand limit. Since the left and the right-hand limits are not the same, the overall limit does not exist. So I can go back up to the top there and just say this limit does not exist. A little aside here, you don't really want to say equals does not exist because that's weird. If I said, oh, you know what, this value equals does not exist. It doesn't equal does not exist, it just doesn't exist. All right, let's go ahead and try this one right here. The limit as x approaches 3 from above. So this is a single-sided limit. So there's only one thing we can do here, evaluate that single-sided limit. And the limit is of the natural log of x squared minus 9. Again, I'll take this in pieces. As x is approaching 3, but from the positive side, or from the right-hand side, I should say, x squared is approaching 9. However, it's approaching 9 from above. That's critical to note here, because if it approaches 9 from below, there's going to be an issue, and I'll showcase that in a moment. As x squared is approaching 9 from above, or from the right-hand side, x squared minus 9 is approaching 0, right? It's 9 from slightly above 9 minus 9. So it's approaching 0, but from the right-hand side or from the positive side of 0. And that's why it's so critical to note that x squared is approaching 9 from above, because 9 from above minus 9 is positive, and the natural log can only take positive numbers as its argument. And so that is a way you can, you have to actually showcase your thought process there. You cannot ignore that. Finally, as x squared minus 9 approaches 0, again, from the positive side or the right-hand side of 0, the natural log of x squared minus 9 approaches. Now, this requires your understanding of the natural logarithm. I've taught long enough to know that there's usually a disconnect for some people coming in. They don't deal with logarithms a lot. Welcome to it. In calculus, you always deal with logarithms. So let's go ahead and quickly graph out the logarithmic function. It's one of the easier functions to graph. It looks like that is a vertical asymptote actually at x equals 0 right here. So you cannot plug in 0, nor can you plug in negative numbers, but you can plug in positive values. And as our inputs approach 0, because that's what's happening here, x squared minus 9 is approaching 0, but from the right-hand side. So as our inputs for our logarithm are approaching 0, but from the right-hand side, our outputs, our y values, are dropping down forever to negative infinity. They just keep falling and falling and falling. So that means that our logarithmic function is tending to negative infinity, which means that our limit, in this case, exists and it's negative infinity. Notice that I said it exists and it is negative infinity. There are some textbooks that say if it's infinite, it doesn't exist. That's a lie. It actually does exist. If your limit is infinite, whether it's positive or negative, the limit exists. It just happens to be infinite. That's all. The only time a limit will not exist is if the limit is not finite and not infinite. As a final example in this video, I just want to bring up some abstract problem here. So calculus is full of abstract and exceptional examples. It is critical that you clearly understand the definitions and theorems presented, because only then will you avoid the pitfalls that entangle so many students. Moreover, because you are playing with infinities, ordinary arithmetic, which is only accurate for finite numbers, falls apart. That being said, suppose you're told that the limit from the right of f of x is infinite, and that the limit from the right of g of x is also infinity. I'm not telling you what the functions are, I'm just saying suppose that they both tend to infinity as x goes to 5 from the right. Is it true that the limit as x goes to 5 from the right of f of x plus g of x is also infinite? Well, think about this logically. And by the way, that's a very difficult thing to do in calculus, because you're playing with brand new concepts, and infinities often defy your basic logic. You have to build up a lot of calculus skill before you really can wrap your mind around the infinite. But this concept, I think, for most people kind of works. So suppose you have something running off to infinity, we'll call that f, and suppose you have something else runs off to infinity, we'll call that g, and you want to add those together. Well, it should make sense that they both added up will become infinite as well. So it is true that f of x plus g of x, the limit of that as x approaches 5 from the right, should also be infinite. So it is true, I'll write that down. And simply said, because infinity plus infinity is infinity. Now, I don't want you to think that I'm doing arithmetic with infinities, because that's kind of illegal. But the reality is, if you have a massive number and you add another massive number, it just becomes more massive. Now, that given an example should actually say give a counterexample if it's not true. So I'm not going to bother giving an example if it is true, because it's pretty straightforward that it's true. But the real reason why I wanted to do this problem is for the part B. Is it true that the limit as x approaches 5 from the right of f of x minus g of x is equal to 0? Remember, f of x is approaching infinity. G of x is approaching infinity. Is it true that infinity minus infinity is 0? So this is something that I want you to think about. Pause the video and just think about that for a moment. Is it true that infinity minus infinity has to be 0? Welcome back if you did pause the video, or if you didn't, shame on you. Here we go. It is not true that that will be 0. It can be 0 at times, but it is not necessarily true that it will be 0. Creating a counterexample can be challenging for a lot of people, but I'm just gonna try to make one up on the fly here. I think this will work. Consider f of x, which is equal to 1 over x minus 5 being cubed, and g of x, which is equal to 1 over x minus 5. Now notice in both of those cases, as x approaches 5, those denominators approach 0. But we're allowing x to approach 5 from the right-hand side, or from above. What that means is x minus 5, in both cases actually, approaches 0 from above. And so that implies, again, in both cases, that those denominators will be positive. So you have 1 over x minus 5 cubed, and as x approaches 5 from the right-hand side, that'll be 1 over 0 with a positive, or in other words, positive infinity. So it does satisfy this condition right here. And with g of x, again, you have 1 over basically 0, but from above. And that will be positive infinity for g of x as well. So we have two functions set up and ready to go. Now let's take a look at the limit as x approaches 5 of the difference of those two functions. I start it this way. I substitute in f and g. I combine the fractions using algebra. And by the way, this brings up something that I normally would say to my calculus students as we move forward. So I might as well start it now. In calculus, it is a really good idea to always think to yourself, perform arithmetic before you perform algebra. Perform algebra before you perform trig, perform trig before you perform pre-calculus, and perform pre-calculus before you perform calculus. So the last step you should ever do in a calculus problem is actually calculus. Everything else should be just arithmetic and algebra. So all I did here was add up a couple fractions. But now if you take a look at this limit, as x approaches 5 from the right hand side, this will approach 0 from above, but that'll be basically 1 minus 0 in the numerator, and so the entire numerator will approach 1, and the entire denominator will approach 0 from above. That's from our earlier work, where x minus 5 cubed was approaching 0 from above. And so this fraction approaches 1 over 0 from above, or in other words, positive infinity. So this is an example where you have two functions that both tend to infinity, yet when you subtract them one from the other, the result is non-zero. In fact, the result is infinite. So I'm giving you a heads up. This type of problem creeps into calculus a lot. So if you have a hard time wrapping your brain around it, I recommend that you see your professor. If that's me, you see me in office hours, ask a lot of questions, really get those clarifications, because this will happen on exams and quizzes. Unless you have an easy calculus instructor, which you should jump out of that class as quickly as possible, because you do not want to learn calculus from an easy instructor, because you'll be sunk for the rest of your college career as far as engineering mathematics goes. All right, that threat being said, I'm done with this video. I hope you enjoyed it, because I certainly did, and I will see you in a future video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.